since usually I walk around a lot, I don't think I can do this today, because then the people who are recording this, they will be unhappy. So I'm trying to stand here. That will be very hard. I work for this company. I guess you know the company. And the most important question of the day, and so this time, at this conference, I'm in an early slot, so it actually makes sense for me to ask the question, who in this room has a Twitter account? It's pretty good. Who's using it? Yeah, all right. Okay. So, because I want you to tweet about this whole event, since you are here, and I hope you're enjoying it, if you like a talk, tweet about the talk that you liked it, so that other people can, I guess, watch the video on YouTube later or something, or so that they come next year, like you did, and enjoy the whole thing in live. If you're going to tweet about my talk, there should be a hashtag up here, and so we're using this one. Yes, exactly this one. So Twitter has a VM team, and I used to say it has a small VM team, but it's not so small anymore. We're about 8 people now, and we have 3-ish GC engineers that take care of all the GC problems that everyone has, right? Including you, everyone has GC issues. Then we have 1-2-ish compiler engineers, and I'm one of them, so I do the fun stuff. And I travel around and tell you about the cool stuff we're doing. Then we have other people working a little bit on infrastructure stuff, and then we have a person working on a tool called AUTOTUNE. And AUTOTUNE is basically the thing I'm going to talk about today, all right? So a little bit about me if you don't know me. I've worked for a very long time on JVMs, and all these 14 years, or is it more now? I don't know. I've been working on JIT compilers, all right? So I'm going to ask you a bunch of questions because I don't know how much you know about compilation and compilers. Who knows what a JIT compiler is? Hey, that's pretty good, yeah. Yesterday I had like 10% of the room. Briefly, because not everyone knows what it is, it's basically, it takes people know what the JVM is, right? JVM, yes, okay. Well, I don't know. Whoever, maybe someone fell asleep from an anatomy course from earlier, waking up, saying, what the fuck? So, JIT compiler, the JVM has JIT compilers. Hotspot, for example, Hotspot is the JVM of OpenJDK. Hotspot has 2 JIT compilers. One is called C1, or client compiler, and the other one is called C2, or server compiler. You might have heard client and server before with the dash client thingy that we used to use a long time ago. Don't do that anymore because it's not necessary. So these JIT compilers take Java bytecode and compile it on the fly, just in time, while you're running your application, right? It's not like GCC where you do AOT, ahead of time compilation. We compile it just in time while we're running. So that's what I do. And I used to work at Sun and Oracle, and I worked in the Java platform group, so I did a lot of Java stuff. Most of these years, I was working on C2, major pain in the ass, one of the main reasons why I'm giving all these presentations about Graal. These are kind of the 3 biggest projects I've done during my time at Sun and Oracle. So I worked on JSR 292. You might notice invoke dynamic language support, method handles if you've used it. We had pretty much 2 implementations. The first one was a lot of handwritten assembly code, and that was a major pain to support and port to other architectures. And then we had some performance issues with that as well, so we re-implemented a lot of the logic that was in the VM before and moved it into Java, into a package called Java Lang Invoke. And I wrote a lot of that Java code as well, so if it doesn't work, you could technically blame me. But as I always say, a lot of people after me touched the code and they broke it and mine was perfectly fine. So then we did CHEP 243 in JDK9, which is, it's a Java level JVM compiler interface. So you need a kind of an interface for the compiler to talk to the rest of the VM. Even C1 and C2 have something like this. It's just in the VM written in C++. So we extracted basically the interface that Graal was already using and made an API out of it. It's not a supported API, right? It's an internal one, but it's kind of stable-ish, so we can since 9, 10, 11, and now 12, it's like the same interface, and you can take one Graal version and run it with all of them, which is very useful. And then we also did chapter 295 in JDK9, which is ahead of time compilation. This is not native image. This is something different. It's basically a small command line utility that loads in class files or char files, sends off compilations to Graal, and then spits out a shared library at the other end. And then the VM can pick up this shared library, or a couple of them, to possibly improve your startup. It's not that easy. Yeah, I shouldn't go into details, but it's very difficult because of the dynamic nature of the JVM. So, I now work at Twitter, the best company on the planet. And you all should create a Twitter account right now if you don't have one, and tweet about only my talk. Don't tweet about anything else, just tweet about mine. This is Twitter. That's what it looks like. At least it did in 2016. We have hundreds of microservices, and they talk to each other, and we have thousands of instances of these microservices, right? And we run on heterogeneous hardware like pretty much everyone does. We own our own data centers, so we know exactly what hardware we have. Ignore the flickering, that's part of the show. And it's probably my adapter, but we don't talk about this. So we know what hardware we have, but if you run in the cloud, you probably don't even know where you are, right? So we're going to talk about performance optimization here. So the number one problem with performance optimization is it does not scale, right? Hand tuning doesn't scale. Usually the way it works is one of you or one of your colleagues at some point in time gets annoyed by the performance of one of your services or whatever you're running, and then you decide to spend a couple hours and tune, right? And then you tune it, and then, this happens every 3 years, I would guess, right? When someone gets annoyed, shit, I'm doing it. But the problem is that you only can do a few parameters, right? Because you have to kind of build up a mental model, and you have to keep track of them, okay, which affects what, and blah, 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 blah. So it's very time-consuming, labor-intense, and error-prone. But the main important one is that upgrades, and we all live in a agile world and blah, blah, blah. You deploy multiple times a day because you think it's cool. We deploy multiple times a week for some of our services, so we're kind of in the same boat. But all these updates make optimality fleeting, right? You tune it today, but the code is different tomorrow. So many services operate below optimality, and that's certainly true for Twitter services. So a little bit of theory, that's kind of the part where I'm faking it a little bit. I know nothing what I'm talking about here. But basically, performance tuning is you have a function, right, over a domain X, and X is basically the space of the parameters you want to explore. And then you want to find a configuration for all these that maximizes F, whatever F is for you, right? It could be you want to increase throughput or reduce latency, or want to reduce CPU. So that's something that we are going to look at later at the experiments that I'm going to show you. It's basically, we are trying to reduce CPU, because that means you save money. If you can use less machines for the same stuff you want to do, that saves a lot of money. So, and important, when you do this, it always is subject to a constraint or multiple constraints. And the number one important constraint is it still has to work, right? And we will also see this later, the experiments that I did, that sometimes you can tune too far, and then it doesn't work anymore. We'll see all this. So performance tuning, that's basically the way it should be working. Iteratively, you pick a parameter or multiple parameters, then you run it on your system, you measure it, you take the measurement, and then a person looks at this and says, I think this was better, so let's try it this way. We would like to replace this performance engineer with, we could use a monkey, I guess, but actually what we want to do is we replace it with a black box tuning. We don't want to know what it is, right? We don't care. The only thing we want to know is which parameter value to try next. That's the only thing we want to know. And we, at Twitter, we decided to use this machine learning technique called Bayesian optimization for this black box thing. So it's a method to learn potentially noisy objective functions iteratively, efficiently. That's important. You know, iteratively, you want to restart your instances, your evaluations, and find and measure them. And efficiently, because we want to be done in a certain amount of time, right? Because if this takes 3 months, then the code is already so different and it changes over time, so it's very difficult. We need it quickly. Finds neo-optima in a few iterations, as I said, very important. Works well with nonlinear, multimodal, high-dimensional functions. High-dimensional is very important because the JVM has hundreds of parameters you could tune. An n-dimensional room. So this doesn't necessarily only have to be the JVM, it could be anything, right? I gave this presentation, guy asked me afterwards, could I tune my database with that? Of course, you can tune anything, whatever. Tune your Minecraft, or, I don't know. As I said, I don't know anything about this stuff, so my colleague Romke, he gave at least 2 presentations, one at Devox in 2017 already. He's the expert on Bayesian optimizations, and he has a very soothing voice, so it's much nicer to listen to him than to me. But if you look at the slides he has here, right, the only thing I did was I stole them. And I'm going to briefly explain to you now how Bayesian optimization works so that you will better understand the numbers you'll see later in the experiments. Okay. So we have a parameter, 1, it goes from -6 to 6, and then we have performance on the y-axis, and higher is better. So the 3 points we have here are actual evaluations we did. So these are real results. This is the actual performance curve that we don't know, right? So the three evaluations we did are certainly on the curve, and this is what Bayesian optimization assumes after it has some data points, what the curve would look like with a certain certainty, and that's the blue area above and below the graph. So overlaid with the actual one, it looks like this. It's not very close, but it doesn't really matter. So what it does then is you basically take the best result you have and you put in a line like this, and then the blue area above the red line is basically the certainty where you would find a better result if you do a run there, and that's the expected improvement graph at the bottom. So the higher it is, the more likely it is that you will find a good result. So all it does now, it gives you back these points, or these values for the parameter, and then you just run it and see how the outcome is. And that's what we did. So we take the one on the right, see, okay, it was slightly worse. We take that one, slightly worse. We take that one, all right, it was a little better. This one, okay, and then we exhausted this space here. And then it looks for the next one, it's the one over there on the right. That sucked, so we are moving to the one on the very left. That was also worse. And so we're going through the whole space until we find the optimum, and that's the one over there. And as you can see, you know, the blue curve, at some point, it gets close to what the actual performance curve is, and that's exactly what we need to do. And a machine can do this for us. So we, as a human, don't have to do it. So we like Bayesian optimization because it's non-parametric, robust, extensible, so it's all very good. Battle-tested on many types of real-world high-impact problems. So Bayesian optimization has been used for many other things, so it works, which is kind of important because we would like it to work. At this point in time, we are not quite there yet, but the goal for this AUTOTUNE tool or service or whatever you want to call it is to be always on in production. That our services constantly tune themselves without us even doing anything. That's the goal. But we're not there yet because there's a lot of, machinery involved that has nothing to do with Bayesian optimization. It's just, infrastructure crap. Good. All right, so that was it. That was the boring theoretical part. Experiments. So AUTOTUNE in general is just Bayesian optimization as a service, as I call it, a BOAS. If you want to tweet that out, please do. We acquired a company a while ago, and the product they had was called Wet Lab. I can remember company was also called Wet Lab, but it's Wet Lab, and that's the Bayesian optimization thing. It's an enhancement of an open source framework called Spearmint. So Spearmint is still open source, it's just not quite as good as Wet Lab, but if we ever, and we plan to, open source AUTOTUNE, on the AUTOTUNE is the driver for the experiments. If we go into open source this, you could technically use Spearmint to do this on your own, because we can't open source Wet Lab, unfortunately. But AUTOTUNE, really, the only thing it does is it talks to the Bayesian optimization thing, gets values for the parameters, and then starts off an evaluation, whatever that is. We run in Aurora on Mesos, but it could be Docker or Kubernetes or whatever, right? You just need to write the backend, or call it a backend, to start an instance. That's all you need. And then you have to have some machinery to get back the value that you're looking for, the measurement thing. That's all you need. You would have to implement this yourself, obviously, but yeah. So that's all it is, really. What is Graal? People do know what Graal is? It's not, I'm not talking about Graal VM. Hands down for the Graal VM people. Okay, good, everyone put his hands down. So I'm not going to talk about Graal VM here, because Graal VM is, and I've said this before and I will say it again, it's an unfortunate marketing term that's very confusing. Graal VM is an umbrella name for 3 different technologies. And one is Graal, the JIT compiler, and we all know what a JIT compiler is now, right? Because I explained it, yes. Truffle, which is the language runtime framework where you can implement language runtimes, and then Substrate VM, which you might know as native image. So these are the technologies. I'm not going to talk about Substrate VM, not Truffle. I'm only talking about Graal, the JIT compiler, and that's the only thing out of the Graal VM world that we're using today. We're just replacing C2 with Graal when we are running with Hotspot. That's all we do. So it's a JVM just-in-time compiler. It's actively developed by Oracle Labs. We all know this. There's an actual open JDK, official open JDK project for Graal, but most of the work is being done on GitHub, and it uses CHEP 243, obviously, and it's written in Java. It's not important for this talk, but it is important if you are interested in trying out Graal. So I have a talk that's called Graal, How to Use the New JVM JIT Compiler in Real Life. And I'm still giving this talk because the main difference between the existing JIT compiler C1 and C2, which are written in C++, is that Graal is written in Java. And at this point in time, there are two major things you should know when you do benchmarking, and it's the fact that it's written in Java, so there's something involved called a bootstrap, which means, since it's written in Java, it has to compile itself when you start up your JVM. So Oracle and Oracle Labs, they're working on solving this issue, let's call it an issue, with a project called libgraal, where they actually just use native image to AUT, compile Graal, and link it to the VM. But today, if you want to use, I don't know, JDK 11, you have the bootstrapping problem. It's not really a problem. I'll explain it in this talk that it's not a problem. And then the other thing you have to know is that Graal, if it does compilations, it uses Java heap memory to do that instead of native memory. But it's, you know, if you know all this, it's certainly not an issue. Good. Okay, so what did I tune? I picked 3 parameters, and I picked 3 inlining related parameters. So inlining, people know what inlining is? Yeah, most people, no? Really? Inlining? Do people know what, yeah, okay. Less than earlier people who knew what a JIT compiler is. So inlining, briefly, a small method that you call, I don't know, give me a good example. I don't have one right now. A very small method that you call from 100 different places, right? That you factored out into a method because it makes maintenance easier. If the compiler can prove that it's better to actually inline that, and that means that you're actually taking the code of the small method and putting it into the caller, that's what inlining is. So you're making your compilation unit bigger. And so you can do more optimizations on your compilation unit. And one of these very important optimizations is called escape analysis. And escape analysis is an optimization that can get rid of object allocations if the compiler can prove that they are not needed. That means you're not allocating objects that are basically temporary, and then you don't have to GC them, you don't have to garbage collect them, and so on and so on. So it's a very powerful optimization. And inlining and escape analysis go hand in hand, because the bigger your graph, your compilation unit is, the bigger the view of the world you have, the more you can prove that an object is actually not escaping. So we were tuning that. I was tuning one that was called trivial inlining size, and it has a default value of 10, and 10 is 10 nodes in the compiler graph. So if you parse in a method, Java bytecode, you parse it into a graph. So the compiler operates on graphs. And 10 nodes in the graph, it's less than 10, we always inline it, because we know it's a very trivial method. And we always want to inline trivial methods, because it's more expensive to call them than to just execute the small, tiny little bit of code they have. The next one, the maximum inlining size, is basically the other end of the spectrum. If it's more than 300 nodes, we don't inline. And then the third one, small compiled low-level graph size, is similar to the second one, but the difference is most optimizing JIT compilers, or compilers in general, have multiple levels of graphs. So there's usually a high-level graph and a low-level graph. And the high-level graph is very high-level. So that's how I explain things, right? The high-level graph is very high-level, and the low-level is very low-level. But the low-level is very close to machine code, right? The high-level is closer to, let's say, what your bytecode instructions are, and the low-level is very closer to what machine instructions are. Okay, so these three we were tuning. And I give another talk that's called Twitter's Quest for Holy Grail Runtime. It's basically the story of me working the first year at Twitter and replacing C2 with Graal and running Twitter services on it. And during the work, during running the experiments for this talk, one thing I did was, I did that what I said earlier you shouldn't be doing. I was hand tuning it, because I wanted to see what could potentially be the improvement that we could get out of this one. So I show you two graphs now. We'll see similar graphs later. So I was comparing C2 for 8 and 9 at that point, because I thought 9 would be coming out. Well, it's the JDK no one ever used. And the purple one is the experiment. So by just replacing C2 with Graal for this particular service, and that's the tweet service, I can reduce GC cycles by roughly 4%, which is great. I mean, 4% is not a lot, but keep in mind, we're still doing the same amount of work, right? We're doing the exact same amount of work, we just use 4% less memory, basically. And by hand tuning, I was sitting down like 3 hours on a Friday afternoon and tuning these 3 parameters you just saw. I got out another 1.5. And I thought, yeah, that's pretty good. And the same for user CPU time. So by just using Graal instead of C2, we can reduce for the tweet service user CPU time by 13%, which is ridiculous. If you've ever worked on compiler optimizations, if you get 1, you're happy. If you get 2, you get home and get drunk. But 13 is like ridiculous. So, and then hand tuning, I got out another 2. And I was very proud of the 2. I thought, oh yeah, that's good. So, but then the machine came in and kicked my ass. So we'll see that now. I defined ranges for the parameters. You don't really have to do this, right? Because the Bayesian optimization will figure it out yourself. You can say 1 to 1,000 or 1 to 1 million, it doesn't matter. It just might take a little longer to find the optimum. The reason why I gave the experiment ranges in this particular case is because I wanted the experiment to end in 24 hours. And I wanted to have this because then the graphs are more readable for the presentation. But I ran the same experiment after, where all of the 3 I said 1 to 1,000, and I basically got the same result. So we're going from 10 to 25, for 2 to 500, 200 to 650, that was default 10, and I knew if we go lower than 10, that's not good. And then this was default 300 and 300. So we try a little lower, but we certainly go higher. The test setup, if you do compiler benchmarking, is very important. So you need dedicated machines. There's no other way around it. Because if you're trying to benchmark a 1 or 2% improvement, that's always in the noise, especially when you have noisy neighbors. I could never run this experiment, and I tried, believe me, in our data center. I don't even know what other services are running on the same machine at that time. So I have dedicated machines, nothing else is running on them. For especially the tweet service, it's very important that all the instances receive the exact same requests. Not only the same number of requests, but the exact same requests, because a tweet could be 1 character long or 280. And the memory allocation pattern would be very different. So we want to compare apples to apples. We ran this JVM-CR version, this Graal version, default tiered C1 Graal setup. I have not explained what tiered compilation is, but it's not really important for this talk. It's basically, no, I'm not going into this. We're just running on Graal, let's put it this way. Okay, experiment 1, tweet service. So the tweet service is my favorite one because, no, not because, it's a Finagle thrift service. And Finagle is one of these frameworks that we developed at Twitter, and it's open source on GitHub. We have a bunch of open source stuff on GitHub if you're interested in whatever. And so Finagle is an extensible RPC system for the JVM used to construct high concurrency servers. I have no idea what it is. I really don't. And I don't have to know. Because the only thing I know, I cannot even write Scala. And this is 92% written in Scala code. That's the important point on this slide. I cannot even write hello world in Scala. And all of Twitter runs in Scala. I don't. Compiles down to Java bytecode. That's all I know. Okay. So, objective. What are we trying to do? We are trying to, this is some Mesos container name stuff, right? We're trying to reduce user CPU time. As I said earlier, reducing user CPU time means less machines, means saving a lot of money. And if you remember, Bayesian optimization always looks for a maxima. So we're just saying 1 divided by, that's all. That's really all. That's all you have to do. And then you need a constraint, at least one. As I said, it should be working, and that's what we're doing here. We're looking for something. In Mesos, you get throttled if you're a bad citizen. And then if you get throttled, it just kicks you out, and that's the one we're using here. I should have been using way more than just one. We do something called redline testing. I'm not sure if other people do that too. It's basically you do redline testing to figure out how many instances you need for your service, so it can process all the requests that can possibly come in on New Year's, as we all know, because everyone, Happy New Year. So that's we should be, oh yeah, redline testing. They have way more constraints, right? Because they know exactly how their service behaves and what needs to be certain values so that it's still fine. I should be using all the constraints that redline testing is using. Didn't have time to do it, but this one is good enough. All right, that's what it looks like. It's 24 hours of tweets, and tweet requests per second. As you can see, the blue one is the experiment, the orange one is the control, and they're exactly the same, and they should be because it's requests per second. And you see like 30-minute slices, and these are the evaluations. So an evaluation I ran for 30 minutes. It's not a very long time, but it's fine for the tweet service. I did this for 2 reasons. Number one, I know the tweet service really well. I know that in 30 minutes it's certainly up and running and at a steady state, and everything's being compiled that needs to be compiled. And the other thing is I wanted it to be done in 24 hours. If we would actually run this, as I said earlier, always on in production, it would certainly be longer than 30 minutes. Because we don't know all the services. We don't know how to behave. We don't know. Maybe it's only at a steady state after 3 hours. You don't know. So it would certainly be longer. Good. So this is the user CPU time graph. And the spikes is basically when we restart the instance because it's compiling a lot. And these are the CPU spikes here. And experiment, again, blue and control is orange. So if the blue line is below the orange one, that's an improvement, right? And so Bayesian optimization goes through the thingy, and you can see, oh yeah, it's better, worse, blah, blah, blah. And then at one point it finds an optima. I don't know where it is, to be honest. It could be the last one, but doesn't necessarily have to be. And this is the outcome what AUTOTUNE gives you. It's basically a website with a table. And it's sorted by the objective, and it's 1.0838. That means we got an improvement and reduced CPU by 8.4%. And this is really good, right? I mean, I could hand tune 2, and this got 4 times as much. And then the second one is like 8.1, and then we have 6.4, 6.4, roughly 6. So let's say maybe the first 2 ones a little bit of outliers, but we at least got a 6% improvement. And that's for free, right? We just tuned it. Yes, so the bottom of the table, we can look at the numbers over there if you're interested, but it doesn't really matter. The bottom of the table looks like this. And as you can see, actually three evaluation violated the constraint. So 3 of them we tuned too far, and I don't know exactly what happened, but maybe they didn't come up, or maybe requests took too long, or I don't know what, but they just didn't work. And then we're going to look at the top, you see there's also like a charts button, so let's look at the charts. They look like this. This is trivial inlining size, but remember, looking at this chart, it's a 3-dimensional space we're exploring. So every data point in this chart has 2 other values that are different, right? So I would have to rerun the same experiment 3 times to actually get charts that make any sense, but it would be different data points, so I'm just showing you this. But we can also already see something even in these charts. If you squint a little, you can see default value was 10, and we start from 10 to, I can't remember what we said, 25. You can see it's actually like going up slightly. So certainly a higher value around the 21, 22 would be better. And the best result we have is basically 21. Then this chart for the maximum inlining size is pretty much flat. We have the 2 outliers out there, which might be outliers or not, because they depend on other values, right? So I'm not exactly sure if they are or not. But again, for the result, it doesn't really matter to me. This one's pretty obvious. We don't even have to squint. So the default for this guy was 300, and 600 is basically where the sweet point is, I guess. Good. So what I did then was I wanted to know, since 30 minutes and all that, is it really the improvement? Do we see that improvement if I run it for, let's say, 24 hours? I was running it actually longer, but I took a 24-hour window out of it. So I was running C2 in blue, Graal with default values in orange, and then the red one is Graal with the AUTOTUNE values. Basically the first entry in the table you just saw. Good. Looking at PS scavenge cycles, so the tweet service is using parallel GC, so these are GC cycles, and you've seen that basically before, the 4.2 number, and now it's 3.4, might be because the code is different now than from the experiments I ran before. It could be anything. But we reduced by 3.4% by just running on Graal. And then with the AUTOTUNE values, it's like that, and it's 3.5 up to a total of 7%. So what's important here is it's nice that we get a 3.5% improvement, 3.4% improvement by running on Graal instead of C2 and get this for free, but we get the same if we tune it. This is enormous, right? So 7% less GC cycles is good, and it's especially good because GC cycles always affect your latencies. So the less you do, the better. Same numbers, just in a different representation. This is allocated bytes per tweet. So if people don't really got the GC thingy, this is how much we allocate per tweet. And important in this one, or interesting, let's put it this way, is it's pretty much flat across the 24 hours. Yes, a tweet can have different lengths, but there's a lot more memory allocation going on the side as well, that it's pretty much flat. And obviously, it's roughly the same performance improvement as we've seen before. maybe a rounding error. Good. This is the one I care about. User CPU time. So in this particular run, and we've seen it before it was 13, now it's 12% improvement. Great, love it. AUTOTUNE looks like that. It's another 6.2 up to a total of 18. And 18 is already like a world. That's a lot. We can, for the tweet service, let's assume we have 1,000 machines. It's actually more than that, but I'm not allowed to tell you. But we can use 18% less. That means, you know, we don't have to buy the hardware. You have to use electricity. We don't have to do the cooling, blah, 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 blah. So all I'm trying to do here really is to save the world. Good. So I also looked at the P99 latencies for the tweet service just to see if the improvements, especially doing less GCs and so on, would affect P99 latencies. And I'm looking at 2 nines only, because if you look at more nines, 3 or 4 nines, you're basically looking at the long GCs you have, and they affect your P numbers. But if you do 99s, it's still 99% of the world and 99% of the tweets, and they actually mean something. So we can see Graal, certainly better. A little tricky to see how much it is. AUTOTUNE, certainly better than Graal, but again, even harder to see. So what I did was I integrated over the whole 24 hours, and that looks like that. And the difference is this. So just with Graal, we have a 20% better P99 latency time. And then we get another 8% out of Graal if we tune it. So we reduce GC cycles, so we have less memory allocation. We reduce CPU by an enormous amount, and even more so, the latency also improves. And 28% means, if you're going to open up Twitter right now, you get your tweet 28% faster. It's ridiculous, right? You could technically then read 28% more tweets if you're fast. The tweet service plus the service we're going to see next, Social Graph. Social Graph, user service, bunch of other, probably 20 at this point. Of these services run 100% on Graal in production for about 2 years. So if you ever used Twitter in the last 2 years, the tweet you saw or the tweet you tweeted was going through code that was compiled by Graal. And we never had an issue. Did you lose any tweets? No. If you did, and that's the good thing about Twitter or some online social media thing, if you lose a tweet, you always blame your phone or your provider. You will never blame us, right? It's like, oh, fuck connection. So, Social Graph. And Social Graph is basically, it's again a finagle thrift service, so based on the same framework as before. It's an abstraction for managing many-to-many relationships at Twitter. It's basically who you follow, who follows you. That's what Social Graph does. And I'm using Social Graph because it has different, yeah, you will see it. It's not, I like the tweet service so much because everything improves so well. For this one, too, but not as much. So again, same objective. We look at user CPU time. Same constraint. We don't want to get throttled. And this is 24 hours of Social Graph. This graph looks different than the one before because it was a different day. October 16th, there you go. Again, 30-minute slots, 30-minute evaluation runs, and this is the user CPU time graph. We've seen that before. Looks nice. This is the table. So the top one is 7.6% improvement. Love it. It's pretty good. Another 7.6, 7.2, 6.8, 6.5. So maybe 6, I would guess. How much was it before? What was the actual improvement then? 6.8 compared to 8 something, I think. That's the bottom of the graph. One constraint, one violated the constraint. So that's pretty good. And the charts, this one looks pretty much, again, this is a trivial inlining size. It pretty much looks the same as with the tweet service. Maybe a little more obvious. And again, interestingly enough, the best result was 23 in this case. But we had 21 before. But around the 22 mark is probably where it should be, at least for our code. but it's 10, right? I would argue if you take all the code in the world, that 10 is not enough, but you know. So this one, kind of flattish again, maybe goes up a little bit as we go higher with the value. This one, not quite as obvious as with the tweet service, but you can still see what's going on. The important bit in this chart is that the result, the best one we have, is pretty much 650. And that was my range. So maybe, you know, the 1 to 1,000 or 1 million would have been better in this particular one. So I'd have to rerun and see if a higher number would get us better results. Good. Same trick. Evaluation experiment. You've seen that before, requests per second. The social graph service is using CMS, so different GC, so we're looking at hard news cycles here now, and we can only reduce by 1.6%. And that has to do with just the code, right? It's just different code. There's a lot of the stack is the same. Yes, it runs on Netty and then Finagle, blah, 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 but the top layer, the business logic is different code. It's like the memory allocation pattern is just different. There's different things. This is with AUTOTUNE, and that's the interesting part. So Graal by itself can only improve by 1.5 or 1.6, but if we tune it, we can improve twice as much, and then up to a total of 5, which is great. But if you would just use Graal or C2 even, you would throw away a lot of the possibilities, or a lot of the performance you would throw away. Because it is money down the drain, because you're paying for your machines, but you're not really using them. User CPU time for the social graph service 5.5 compared to 13 earlier with the tweet service, so certainly less. AUTOTUNE 7.8, that's pretty good, up to a total of 13. Interesting thing I should mention on this slide is if you look at, you know, the gap, the difference between blue and orange, it's pretty much the same. It doesn't depend on the load. But with the AUTOTUNE, it does depend on the load. As you can see here on the left, when the load is low, we get less improvement than when the load is high. And the 7.8 I took where the load is high because I want to look cool on stage. I'm not taking that one. I don't have an explanation for this. I didn't have time to look into it, but it's at least interesting. But that should not happen if you ask me. But again, 13%, I totally take it. Questions? There should be, only one person has a question, but probably, I hope everyone is thinking this question, right? So, I mean, he's standing there and talking about all this Graal stuff, and what about C2? Well, yeah, of course I did. I could not come up here and have a presentation about this stuff and not do the same AUTOTUNE experiment with C2. That would be stupid. Okay, so these are the 3 parameters that are tuned for C2. One is called max inline level. Graal does not have that. It's basically how deep inlining goes, how many levels of inlining you do. So that means if you, and I think everyone does this in this day and age, if you use a lot of frameworks and you call your framework and that framework calls the other one, call, at 9 it stops, right? So you might not even inline the actual logic that you're trying to inline, the one you wrote, because there's a lot of layers in between. So, and 9 is not a lot. Max inline size is pretty much the one that Graal has as well, the one that had 10. But this 35, the main difference here is this is bytecode size. Before it was nodes in the graph, we actually parsed the thing, we had nodes in the graph. This is bytecode size. If you ever wrote code, a small method, let's say, and then you added some assert statements to that method, and for some reason it suddenly became more than 35 bytes, it's not inlined anymore. At least then it depends on other things. So that if you suddenly see performance regressions when you add assert statements, that's a problem. And C2 doesn't discount assert statements in bytecode, and we never fixed it, and I'm very sorry about this, but the solution is to use Graal. Thank you. Inline small code, it's a very weird one. Graal doesn't use that either. This number is native code size. So 2,000 bytes of compile code. And the reason for this one is it's kind of weird. To some degree, it makes sense, but not really. If C1, I should have explained to your compilation earlier, shit. C1, if C1 compile, if there's already code compiled by C1 and it's bigger than 2,000 bytes, C2 will not inline that method. And I think the logic behind this, the reasoning is, if it's 2,000, it's probably pretty big, we don't want to inline it. Which is not always true, but okay, I'll take it. Good. I gave it ranges again because I wanted it to finish. For the inline level thing, I actually went from 5 to 20 because I wanted to see what happens if we go lower. Right. So fire alarm? We hope not. Oh, my keynote just crashed. It was a fire alarm. All right, where are we? Somewhere down here. Where are we? No, not that far. Here. That looks pretty good. How about this? Can you put it back on? My phone just dropped. No? Yes? No? No? Is it not working? Let me try to unplug and plug in again. I can see it here on this monitor. Ah, perfect. Okay, here we go. Requests per second for the tweet service with C2. Again, 30-minute evaluation runs. That's the CPU time result graph. And here is the table of the result. So the best result we have is 5.1, which is pretty good, right? I mean, AUTOTUNE, and remember this talk is actually about AUTOTUNE. AUTOTUNE certainly did its job, right? It could tune 5% out of C2, which is around for a very, very long time. The next one is 3.8, 3.5, 3.3. So I would guess the 5 is an outlier, and maybe we'll get 4 if I'm very nice to C2. This is the bottom of the table, no constraint violated, and these are the charts. So this is the inlining one I was talking about, right? You can obviously see what the hell's going on. The default value is 9, and I would argue it should be 17, probably for most code in the world anyway, because 9 is just, we set 9 10 or 15 years ago, right? Code changed a lot since then. This one, max inline size, is flat. That doesn't surprise me too much because if methods get bigger, we rely way more on profiling information, and then profiling information gives us the actual information that we need, so this one doesn't surprise me too much. And this is the inline small code guy. It's pretty much flat, so it's not a big surprise that this one didn't affect it at all. I did not do a verification experiment for C2, but as I said earlier, we might get a 4% improvement, and that would be cool. But compared to what we can do with Graal, it's just not as close, right? We got how much was it, 6.8, I think, with Graal for the tweet service improvement by tuning it, on top of 12, right? So it's like it was 18, and with C2 we get like 4, if we're lucky. So there is the summary of my presentation, and it's the summary of all the presentations I'm giving. It's this, and it's basically, that's the way how you turn on Graal. And I'm giving all these presentations for mainly one reason, and I want you, since today's Saturday, if you go to work on Monday, I want you to try Graal. If you're running Scala code, you certainly are obligated to try it. I've never seen Scala code that runs worse with Graal than C2. It was always better and always faster. With Java code, it's a slightly different story. I've seen, and we at Twitter, most of our services are written in Scala, but we have a few that are written in Java. And we've seen substantial improvements for the ones that are written in Java as well. It's just let's say a 50-50 chance if your code will run, if your Java code will run better on Graal than on C2. And it has two reasons. And the one reason is C2, and I worked on C2 for many years at Sun and Oracle. We've never spent a single day or a single hour to optimize for other code than Java. Never. So if you're running anything else than Java, you would certainly use or try Graal. The other reason why Graal cannot easily be better than C2 on Java code is the Java code that has been written has been optimized for C2, right? Because you write it so that it's the fastest on what you have today. And it's very difficult for a new compiler to come in and be better everywhere suddenly, right? So please try it out. I know you, so if you run on JDK 10 or later, you just download the JDK, open JDK, it has Graal in it, you turn it on with this, and I'm sure every one of you is running JDK 11 in production. Exactly, like we do not. We also are on 8 for quite a bit, I think. But there is an open, a JDK 8 bundle that you can download from Oracle Labs. You'll find it. I think graalvm.org will give you something. Just be careful which one you download, because there's a community edition and an enterprise edition, and enterprise means you have to pay money if you use it in production, so don't, you know. And it's Oracle, so they'll sue you. Don't do that. And yes, so please try it. I'm sure it's very easy to turn it on in production. Probably not. But everyone has some sort of staging environment, right? You're going to test your stuff before you push it out to production. So maybe you can turn it on there. Turn it on, see what it does. Maybe it's better. If it's better, let us know. That would be great. If it's worse, please also let us know. Because we want to improve Graal. It might be difficult, I understand this, if it's some business logic with, you know, proprietary code that you cannot share it, but maybe you could extract a test case so we can see what the problem is. If it crashes, that's perfect. That's exactly what I want. Please file a bug on GitHub. Because if it crashes, that means we've found a serious issue. Graal, and I said it earlier, we run on it for like 2 years. And the last bug, if you watch the one talk, the Twitter's Quest for Holy Graal Runtime, we found a few bugs when you started running things on Graal, but only like 4, and I explain all 4 in the talk. But since then, nothing, right? You know, our code, sure it changes, but not too much. And then Oracle Labs, they're only running their spec GBB for the millionth time. They're not going to find any other bugs. So what we really want is that you run your shitty production code on Graal, because they will trigger the edge cases. So I would be very happy if you could do this, and if you find a bug and it crashes, that would be great, because that means, well, we don't find the bug, and if Twitter is down, I'm in hell. Okay, so let's not do that. Let's all work together that my life is good. And I think I'm kind of out of time, yes. And that was actually it. So if you have questions, come to me, I'll answer everything. Tweet me, send me a DM on Twitter if you need help running it or whatnot. Thank you very much.